All right, so in this section we're going to learn about the Chinese remainder theorem, which will give us an efficient way, a more efficient way to decrypt messages that are encrypted with RSA. So it's a really old problem, it's a really old result, and it's usually presented in the form of this kind of riddle or puzzle. And here we have a bicyclist runs into a woman who's carrying a basket of eggs and breaks all of them. He feels awful, so he wants to pay for the eggs, but she doesn't remember how many there were. For some reason, though, she knows that if she took the eggs out 3 at a time, she would be left with 2. And if she took them out 5 at a time, she'd be left with 3. And if she took these same eggs out 7 at a time, she would be left with 2. And, you know, just set aside the incredulity of the scenario where she would happen to know this information but still not know how many eggs that she had in her basket. We can rephrase it as follows. Is there a positive integer x such that when x is divided by 3 it yields a remainder of 2, when it's divided by 5 it gives us a remainder of 3, and when it's divided by 7 it gives a remainder of 2. And we can boil it down even more. We have the mathematics to kind of state this in another way. We want to know, is there a single integer x that's equivalent to 2 mod 3, and also 3 mod 5, and also 2 mod 7? So the question about whether a solution exists is what the Chinese remainder theorem is all about. So what we have here is a system of congruences that we're looking at, right? 3 congruences. They're all mod a different number. And it simply says that if I have a system of congruences like this, right, so here's one, right, x is r1 mod m1, it's r2 mod m2, and it's rn mod mn, and maybe a bunch in between, right, so maybe I've got a bunch of these. If the moduli are pairwise relatively prime, then there exists a solution, and it is unique mod the product. So if we apply the Chinese remainder theorem, the theorem doesn't say what the solution is. It simply guarantees that there is a solution if the modulus numbers are relatively prime. So up here our modulus numbers are 3, 5, and 7. Those are pairwise relatively prime. Pairwise relatively prime meaning that no 2 of them share any divisors. So the Chinese remainder theorem, which I'm going to abbreviate CRT, says that there is a solution that exists to this system of congruences, and that solution is unique mod the product 3 times 5 times 7. Uh, 3 times 5 times 7, which is 105. So maybe there's lots of integers that would satisfy these criteria, right? That would satisfy the 3 congruences, but there's only one mod 105 that makes it work. So our technique to solve these system of congruences will involve just repeated substitution. So it's basically just some algebra and remembering what it means to be equivalent to, say, 2 mod 3 or 3 mod 5. So let's begin. In our first part here, I'm going to number these congruences. So there's the first one, there's second, there's third. So here's how we start out. I'm going to take this first equation, x is equal to 2 mod 3. I'm going to rewrite it. If it's 2 mod 3, that means it's 2 more than a multiple of 3. So we could say that x is 3 times some integer r plus 2. Now, next what we do is we substitute this expression for x into this congruence in the second equation. So this gives us, we started with x equals 3 mod 5 in the second one. So now I'm going to have 3r plus 2. is equal to 3 mod 5. And we're going to solve this congruence for r. So we could subtract 2 from both sides. And we get 3r is 1 mod 5. So if I want to solve this, I need to know what the inverse of 3 is mod 5. And you might recall we actually figured this out before, but that inverse is 2, because 3 times 2 is 6, and that's 1 mod 5. And so we find that r is 2 mod 5. Okay. Now if r is 2 mod 5, I'm going to rewrite what does this mean. If it's 2 mod 5, it's got to be 2 more than a multiple of 5, so r is equal to 5s plus 2, where s is just some integer. And now I'm going to go back to this equation up here. So our third step is to plug this into the equation from step 1. So up here we have x is 3r plus 2, and I know that r is 5s plus 2, so I'm going to plug that in. And then plus 2. I'm going to do some algebra. I'll expand this out. 6 plus 2, 15s plus 8. So now I have another expression for x. X is 15s plus 8. I'm going to scroll up. Our next step, we're going to pull in now our last congruence equation. So now we're going to plug x equals 15s plus 8 into the third equation. So x is equal to 2 mod 7. That means we get 15s plus 8 is equal to 2 mod 7. Now look, this equation is mod 7, so I can reduce everything mod 7. 15 is 1 mod 7. So this is just 1s. 8 is 1 mod 7, so that's 1. So I'm just reducing mod 7 first. You don't have to do that, but I think it makes things easier. Now all we have to do is subtract 1. And we see that s is 1 mod 7. And if you're equal to 1 mod 7, that means you are 1 more than a multiple of 7. So s is some multiple of 7, say 7t. Plus 1. And now we can finish this up. In our fifth step, we're going to plug s equals 7t plus 1 into the equation for x that involves s. So that's up here, right? So we get x equals 15 times 7t plus 1 plus 1. So 15 times 7, that's 135. T plus 15 plus 1, or 135t plus 16. Now we've used all of our equivalences, or all of our congruence equations, and we have a result. If there were another congruence equation, we'd take this and plug it into another one. This technique can accommodate as many equations, or as few equations as we have. But we've used all of our equations. We now have our expression for x. And if x is 135t plus 16, that means it's 16 more than a multiple of 135. And so our final result is that x is 16 mod 135. So that is the result that is unique mod 135. There are many integers that will satisfy the three congruence equations, but they are all of this form. Every integer that satisfies those three equations will be 16 more than a multiple of 135. Let's do another. Again, we start with three congruence equations here, so I'm just going to number them. We're going to go and use the same process. And I'll note, actually, before I start, I want to just take note of these modulus numbers, the moduli, 5, 7, and 11. They're all distinct primes, so they are all pairwise relatively prime. We don't require that the modulus values themselves be prime. But certainly if they're all distinct primes, then that satisfies the criteria. All we need is for none of them to share any factors with each other. So let's begin. Again, we're going to start. X is 3 mod 5. That means that it is 3 more than a multiple of 5. Then I'm going to substitute this into the second equation. So the second equation is x is equal to 2 mod 7. So now we get 5r plus 3 is 2 mod 7. We're going to solve this. Now instead of subtracting 3 this time, because that would give me a negative, I'm going to add 4. Right, because adding 4 would bring us to 7, and that's 0 in this equation. So we find that 5r is equal to 6 mod 7. I need the inverse of 5 mod 7. You could use that, you could use the extended Euclidean algorithm, or you could use these are small numbers, so you could just sort of guess and check, or use that little program. But you should find that the inverse of 5 mod 7 is 3, because 3 times 5 is 15, and that's 1 mod 7. So we get r is equal to 18 mod 7, and then we're going to reduce. We get mod 7, that should be 4 mod 7. Now if it's 4 mod 7, that means it is 4 more than a multiple of 7. So r is 7s plus 4. And then I'm going to take this expression and plug it into the equation up here from step 1. So that's what we're going to do next. So x is 5r plus 3, so that's 5 times 7s plus 4 plus 3. So distributing the 5, 35s plus 20 plus 3, so 35s plus 23. Okay. Now, let's pull in that third equation. So we're going to plug x equals 35s plus 23 into the third equation. So that looks like if x is 7 mod 11, then we have 35s plus 23 is equal to 7 mod 11. Again, I'm going to reduce mod 11 before I solve. It'll just make it easier, I think. So 35 mod 11 is 2. 23 mod 11 is 1. So I'll subtract 1. And now I need the inverse of 2 mod 11. Again, you can use the extended Euclidean algorithm, or or guess and check. I mean, or the program, it's already, 11 small, so it wouldn't take too long just checking each option. But you should find that 6 is the inverse of 2. 6 times 2 is 12, and that's certainly 1 mod 11. So we get S equals 36 mod 11. And 36 mod 11 is 3. Okay, now we're almost done. Oops. Step 5 here is that we want to get, now roll this into our expression for x. So I guess before we do 5, I'll just say the last thing is if it's 3 mod 11, that means it's 3 more than a multiple of 11. So 11t plus 3. So our last step here is plug 11t plus 3 into S into the equation we have for x, 35s plus 23. So we have 35 times 11t plus 3 and then plus 23. Thirty-five times 11 is 385. 35 times 3 is 105. And then add 23. 385t plus 128. Yeah. And so every integer that satisfies both, all three of those congruence equations will look kind of like this. That means that this solution is unique mod 385, which is the product of the modulus values. X is 128 mod 385. With these types of problems, I mean, the answers, they're at least easy to check. I mean, we have a value for x. So you can, use the mod program or calculate it, use the division algorithm, but you should find that that 128 is 3 mod 5, it's 2 mod 7, and it's 7 mod 11. Okay, so here's why we care about the Chinese remainder theorem. It offers a more efficient way to decrypt a message in the RSA crypto system. So remember that decrypting a message in RSA involves calculating c raised to the d power mod n. That's a bad line break, so I'm going to fix that here, mod n. And where n is the product of two very large primes, right? N is equal to p times q. Now, the Chinese remainder theorem says that if I were to look at this system of equations here, that c to the d, which is equal to some value r1 mod p, just the prime p, and then c to the d is r2 mod q, then there is a solution that is unique mod their product, that is unique mod n. So if I can calculate both of these values, the r1 and the r2, then I can just solve the system of congruences to figure out what c to the d power is mod n. Now, at first, that by itself might not seem like much because we're just replacing one kind of fast exponentiation process with two. And it might not, c to the d is like large probably. What makes this efficient, what actually helps, is that since p and q are both prime, we could take advantage of Fermat's little theorem. Remember, Fermat's little theorem says that a to the p minus 1 is equal to 1 mod p. And so to know the value of c to the d mod p, we only have to figure out what is c to the d, we only have to figure out, if you look at the power, we can reduce the power mod p minus 1, right? Just whatever multiples of p minus 1 exist in the power, those raised to that power are equal to 1 mod p, right? We actually saw some examples of that in the last section. So it will actually drastically reduce the power that we need to raise c to, and while we're at it, we can reduce c mod p as well, right? So as we're going through, so we can reduce the base mod p, we reduce the power mod p minus 1. And this is what actually helps make it more efficient. We're going to be doing it by hand, and so you might even question, is this even that efficient, much more efficient? I would say it is, even when we're doing it by hand. It is absolutely for sure more efficient when you consider that in practice this decryption is done on computers, and computers can run both of those calculations like in parallel. So we're going to do a decryption example. So Bob picks a couple of primes, 61 and 53, and his encryption key E is 17. So here's what he tells everybody. There's his encryption key. 3233 is the product, 53 times 61. And then he computes his decryption key. And so you recall we did that in the last section, right? So D is just the inverse of 17 mod phi of n, and he finds that D is 2753. So he encrypts a message and sends it to Alice. The secret message is 1039. He uses modular exponentiation and computes 1039 to the 17th power mod 3233, and he gets 349. He uses fast exponentiation to do that. So Bob gets the secret message 349. Now, to decrypt the message, Bob has his own decryption key. He knows what it is. And D is 2753. So decrypting involves making this calculation, right? C to the D mod n. We can do this a little bit more efficiently by replacing that with these two calculations. It's the same power, right? It's still 349 to the 2753, but we're going to evaluate it mod 61 and then mod 53 separately. So let's begin. The first part, okay, so I'll do that one first, is 349 to the 2753 power mod 61. If we're using the Chinese remainder theorem, and in fact, we're using the Chinese remainder theorem, and that's why we're splitting it up. Once we look at the individual ones, what we're going to do is use Fermat's-Little theorem. Fermat's-Little theorem says we can reduce the power mod phi of p, so I can reduce this mod 60. And in any congruence equation, I can reduce any, the base mod p, so we're going to reduce this mod 61. So 349 mod 61 is 44, and 2753 mod 60 is 53. So right out the gate, I get to take this calculation 349 raised to the 2753rd power, reduce it to 44 raised to the 53rd power, and that's helpful. Now I'm going to use fast exponentiation on this. We'll note that 53 as a sum of powers of 2 is 32 plus 16 plus 4 plus 1. And so the desired factors, when I write out this 44 to the 53 power, that's 44 to the first times 44 to the 4th times 44 to the 16th times 44 to the 32nd power. Those are the desired factors. And we're going to make our little table. Okay. And in this calculation, we're going to reduce everything mod 61 as we go. Our total always starts at 1. Our first factor is our base to the first power, 44 to the first, which is 44. This is a desired factor, and so our total changes, and we get 44, which is already reduced mod 61. Our next factor is 44 squared. Reducing that, mod 61 gives us 45. Not a desired factor, so our total holds at 44. Next factor, 44 to the 4th, which is 45 squared. That gives us 12. This is a desired factor, so our total changes 44 times 12 mod 61 is 40. Our next factor is 44 to the 8th, which is 12 squared. Reducing that, mod 61 is 22. This is not a desired factor, so our total holds at 40. Our next factor is 44 to the 16th, which is 22 squared. Squared mod 61 is 57. This is a desired factor. We're going to change the total. And last, 44 to the 32nd power, that's 57 squared. Squared mod 61 is 16. That's desired. It's our last desired factor. So 23 times 16. Oops. Okay, so I'm going to go back, I'm going to scroll up briefly here. I'm going to come right back down to this table, but this value that we want, right, this one here that we've been highlighting in yellow, or that I highlighted in yellow right up here, I'm going to call this X. So that what I want to find is X mod 61 and X mod 53. And that's how I'm going to be able to use the Chinese remainder theorem. So this value X that we just found, this 349 to the 2753, we evaluated at mod 61. We found that it is equal to 2 mod 61. Okay, now we're going to do this one more time because we have to evaluate it mod 53 as well. So our second calculation, 349 to the 2753 mod 53. Now we get to reduce the base mod our prime 53. So 349 mod 53 is 31. And now using Fermat's last theorem, this is like the powerful part, is I get to reduce this exponent. Reduce mod phi of p, or q, or whatever, right? So phi of 53, 53 is prime, so phi of 53 is 52. And 2753 mod 52 is 49. So I want 31 to the 49 power mod 53. So we've used Fermat's last theorem now to restate this computation we want to make, and it makes it a smaller problem. So 49 is equal to 32 plus 16 plus 1. There it is as a sum of powers of 2. So that means that 31 to the 49 is 31 to the first times 31 to the 16 times 31 to the 32 power. And we're ready to make our table. We're going to do all calculations in this table, mod 53. Our total always starts at 1. Our first factor is our base to the first power, which is 31. That is desired. Our new total, 1 times 31, is 31. Next, we're going to square, so with 31 squared, mod 53. That's 7. Not a desired factor. We're not going to have another desired factor until we get to 31 to the 16th power, so our total holds here at 31. 31 to the 4th, that's 7 squared, which is 49. Already reduced mod 53, not a desired factor, so we hold at 31. 31 to the 8th is 49 squared. Mod 53. That's 16. Still not a desired factor, so our total holds at 31. And then last, let's see, we get to, oh, not last, but we're at least getting to a desired factor. 31 to the 16th is 16 squared. Mod 53. 44. This is desired. So 31 times 44 is 39. And then now our last factor, 31 to the 32 power, is 44 squared. This is desired. 39 times 28 is 32. Okay, so we're done. That was our last desired factor. This total is our final total. So we found that this value x that we're looking for over on the left, we found that it's equal to 2 mod 61. Here we know that it's equal to 32 mod 53. So now is when we're going to use the Chinese remainder theorem. We're going to solve this system of congruences, and the Chinese remainder theorem guarantees that a solution exists and that that solution is unique mod the product 61 times 53. Mod PQ. And for us, that's mod 3233. Okay, so I'm going to start on the left side here. To x is 2 mod 61. That means it's 2 more than some multiple of 61, so 61r plus 2. Now I'm going to take this expression for x. I'm going to use it to rewrite this congruence equation. So 61r plus 2 is equal to 32 mod 53. And I'm going to do two things here. Well, I guess maybe I'll do them one at a time. Let's reduce mod 53. 61 mod 53 is 8. So 8r plus 2 is equal to 32 mod 53. I'll subtract 2. R is 30 mod 53. We need the inverse of 8 mod 53. We can use the extended Euclidean algorithm for just the sake of saving time right now, because 53 is relatively small. If this were much larger, I would absolutely just use the Euclidean algorithm, because that would probably be faster. But this is a pretty small number, so I'm going to use this inverse program. Oops. And I need the inverse of 8 mod 53. And we get 20. So I'm just going to make a little note. 8 inverse is equal to 20 mod 53. So I'm multiplying both sides by 20. On the left side, 8 times 20, I know that's 1. That's how I chose 20. And on the right side, 30 times 20 mod 53 is 17. Okay, so if r is 17 mod 53, that means that r is 17 more than a multiple of 53. So say 53s plus 17. Now I'm going to take this expression and plug it in for r up here. Do some algebra to expand this out. 61 times 53 is 3233. 61 times 17 is 1037 plus 2. 3233s plus, and then plus 1039. So there's x, and look, what we just deduced here is that x is equal to 1039 mod 3233. And that means that the decrypted message is 1039, which is what we should have gotten. Victory.